let's recap our discovery, basically, of the Biot Savart law. So what this law allows us to do is to calculate magnetic fields. It is the direct analog of Coulomb's law. If you remember our discussion of the electric field, things are very analogous. For the electric field, we knew how to compute the force on a charge once we had the electric field. Similarly for the magnetic field. But then that leaves the question, how do we calculate magnetic fields? And the answer to that question is the Biot Savart law. And the way this law works, I've written it out for you here in terms of how we basically began by deriving it. If you recall, we had considered a long infinite wire, and we noticed there was this intriguing relationship between the magnetic field and the electric field we would expect from such a wire if we generated the current by simply allowing the charged wire to move. And that relationship basically was that, apart from some constants out in front, that the magnetic field is at right angles to what we would expect from the electric field. Hence, we have this cross product with the velocity. And that indeed, what enters into the calculation then is the electric field from each of the charges making up the wire. So this was the formula we had come down to, where here what you see is your standard result for Coulomb's law. Over here on the right, I'm reviewing with you the geometry. We're imagining some origin here, indicated with an O. Our point where we're trying to calculate our magnetic field is the point R, represented by a vector R. And what we are doing is summing the contributions from a whole series of charges labeled by I, each of which contribute to the field at location R. The variables then refer to each charge I. The vector R sub I tells you the location of the given charge. Q sub I is its charge. And because we are talking about magnetic fields, the velocity definitely enters into the equation, and the velocity of the corresponding particle we denote V sub I. So we immediately, though, moved away from this kind of a theoretical form. We had gotten this by trying to align our expectations of what the formula in general should look like with what we knew it was specifically for that wire example. And what we learned was, if we simply took the result from the wire example and realized that, well, we don't want to just use one single velocity v, but in general we would expect it each contribution from each charge to depend upon its own velocity, v sub I. We then would immediately simplify this by canceling out the permittivity constant epsilon naught, leaving then just the permeability constant mu naught on 4 pi, then multiplied by a sum over all of the charges of this product that we constantly see in magnetic field theory, the charge times the velocity of each particle, then crossed basically in the same form of what we usually see in the Cartesian form for the electric field. So it's deeply analogous. The main difference from the electric field is the appearance of this velocity vi, and it always seems to involve some sort of a cross product, as I've given you here. Now this form, as you see, is very analogous to the Coulomb form, with the displacement vector starting at the charge that's contributing to the field, and then extending off to the location where we are calculating the field. That's this displacement vector divided by the cube of its length. In Coulomb's law, remember, we had an alternate form, which is often useful, the so-called trig form. And in this form, what we do is we take one factor of distance here, divide our displacement vector by it, and that allows us to define a direction vector, r hat sub I. This is the direction that points from the contributing charge towards the location where we are calculating the field. And then what's left from the denominator, because we've used one factor of distance to define this unit vector, we're just left with the square of the distance. Again, very similar to Coulomb's law. The next maneuver that we made is we noticed, well, we have this sum over individual charges times their velocities. In practice, that can be very difficult to track the motion of every last single charge in a system. So we use the theorem that we had derived previously when we looked at forces on wires, where we realized that sums over whole sets of moving charges can be replaced then with integrals over then, if it's a wire, we integrate over the length of the wire, and we replace the sum with the integral, and the product of charge times velocity then becomes simply the current traveling down the wire I times a displacement vector representing each little chunk of the wire, and the direction of that vector then represents the direction of the flow of the current, and it's also, of course, then the average drift velocity of those particles, so that QV gets replaced with IDL, and then we have the rest of our formula remains intact. There's one final alternate form which we discussed, which is useful when we're talking about more general situations where we don't have just a single very narrow wire so that we know the direction that every single charge is traveling, but if we're integrating here over some kind of a volume, here I'll give you some kind of strange volume conductor where the current density J might point in different directions with different magnitudes at different locations within this strange shaped material. In that case, we would integrate over the entire volume of the material. What the current times distance then becomes current density times then volume instead of distance. But the remainders of the formulas remain intact. Finally, we noted that you could use this trig form for these integrals, or you can directly convert to the Cartesian form using our standard relationship between those two different forms. So, what all of that then gives us at the end of the day is a series of useful formulas. Which one we use would depend upon what types of information we have at hand, but a series of different closely related formulas that allow us to calculate the magnetic field for any type of a situation. So, this is like having Coulomb's law for calculating electric fields. The next thing, of course, you do once you have a law like this is you want to start trying to use it. So we work through an example to show you how to employ the mathematics of this law. So what we did was we took our standard example that we've been using in our entire discussion of magnetic fields, which is simply to have a current-carrying wire carrying current off to the left along the x-axis, as I've indicated here. And then we're going to ask and inquire about the value of the magnetic field vector at some location at a distance y up along the y-axis above that wire. We carried through the integral in the Biot Savart law. I'm not going to review all those details again for you, but long story short, this dl represented a series of little chunks as we divided up our wire along the flow of the current. We then defined angles so that we could appropriately take cross products of that dl with the unit vector pointing then from the source of the field up towards the point where we're observing the field. We then carried through the integral, and the result that we got was a very familiar result. It was very satisfying that the same result that we've been quoting to you over and over again, we were able to recover directly from our Biot Savart law, so we're no longer dependent on just being told the field for this particular situation. And what we learned in this case was that indeed the magnetic field at this location y proves to be into the page, as we denote here by the minus k hat direction, and its magnitude also is just what we've been exploring and discussing with you, namely it's the permeability mu naught times the current divided by this famous factor now of 2 pi times the distance in this case being y. So that is what we have learned so far about and through the Biot Savart law.